All right. So let's go ahead and get started. I'll finish off homework number 7 material today. And then we'll just continue right through to homework 8. It's not going to be a major change or anything like that. In fact, homework 7 and 8 kind of continuations on the same stuff. So that's what we're up to, along with the heat engine lab this week. And I think if my calendar is correct, I think we're due for the exam. Actually, let me check here real quick. I think we're due for the second exam 2 weeks from today. Yes, we are. So that's November 16th. Okay. So exam number 2. That's November 16th and 18th for those of you that are in the Friday lab. So that's in 2 weeks. That covers homeworks numbers 5 through 8. So basically, it's the entire thermo unit. Okay? So it's kind of a nice block of one topic for the second exam. So I'll make practice materials available shortly, and I'll assign homework 8 today, and that will be coming up. Question?
So it's not including light?
Correct.
Okay.
Yes. Light will be the stuff we do after the second exam. That will be on the final exam. It will include light insofar as that's relevant to radiation. Okay, so let's just jump right in. The last thing we have to do to predict the heat capacity of a monatomic solid by way of counting the degrees of freedom. So let's do that. So again, we have 3 different temperature regimes: low, medium, and high. So these are plateaus where we can basically pretend, we can say that we have a relatively constant heat capacity before we then move on to the next plateau where further degrees of freedom are quote-unquote unlocked or unfrozen, okay? So as to how long these plateaus last, it depends on the material, but we're not going to get into all that stuff. We're just going to say we're squarely in the low, medium, or high temperature regime. So we learned that it's all about translational degrees of freedom at low temperature. Then we had rotational degrees of freedom get unlocked next. And then vibrational degrees of freedom are the hardest to access. They're the highest steps of the ladder. And here it proceeds very differently to a gas because we do have a solid. We have a monatomic solid. It looks something like this, okay? So all the atoms, these are individual atoms. We don't have different types of atoms. It's a single type of atom, but they're all in a solid grid like this. This thing doesn't come apart. So first of all, translation. Individual gas particles can move around the whole container. These cannot. This whole chunk does not move, okay? So this particle does not have freedom to wander around anywhere it wants. It's more or less stuck in place, right? Of course, it doesn't exactly get stuck in place unless it's absolute zero. The only thing it can really do is vibrate here. So we don't have access to translational, because of course these can't all move. We don't have access to rotational, because these can't all rotate. So right away, we don't have any of these, we don't have any of these. A given atom, the only thing it can do is vibrate. By definition, the moment it moves against a chemical bond that's right next to it. But unlike the diatomic, where there was only one vibrational mode, right? It could oscillate like this. Let me see if I still have that one. There we go. So unlike the diatomic, where it can only vibrate one way because it has one buddy to vibrate with, this has neighbors on all three spatial dimensions. So it can vibrate back and forth, it can vibrate up and down, or back to front. So there are actually three different simple harmonic motions that it can undertake, right? So we have three vibrational degrees of freedom, okay? And each of those comes with a K, and it comes with a potential energy, as we learned, okay? So when we get to those each vibrational degree of freedom comes with a kinetic energy and a potential energy. So let's work out the energy. So what's the total energy contained here? So we have our equation here, which we've been using for kinetic energy. The degrees of freedom is 3. And then every single one of those has an associated potential energy. So we get another bit of energy from the potential energy. So then we get, if we add these two together, we get F times nRT, and the F here would be 3. So the halves went away because I just combined them, okay? So again, F is 3, but I don't want to put it in quite yet. And then from there, once we know the total energy, which that is in itself is useful, if I ask you for the total energy contained in the monatomic solid because of its temperature, you just put in the temperature, how many moles you have of it, and the degrees of freedom of 3. And then we're going to go ahead and set it equal to good old Q minus W. Well, I guess I have to make it delta first. So delta E, which is FNR delta T, equals Q minus W. So as always, it's probably easiest to say it's an isochoric process, because then there is no work. And then we go over here. Of course, we have N cancels with and delta T cancel. And we have CV is F times R. Okay? So now at this point, I can put in the degrees of freedom, and we arrive at CV is 3R. So that's a number, and that number is 24.93 joules per mole Kelvin. We are predicting that any monatomic solid has this molar heat capacity at constant volume. So how do we get CP? What?
CV plus 1.
What's that?
CV plus 1.
Aha, yes. We usually have been using that formula. Why can't we use that? It's a solid, not a gas, right? Remember, the whole reason why CP is CV plus R is when you have a gas, right? And the whole idea was that if you're adding heat when it's an isochoric versus an isobaric process, you get very different delta T's. So just to remind you what happened there, when we had a constant pressure process, we put in heat, but we got much less delta T, because why is that again? Some of it goes out as work, right? That's why CP was greater than CV. Well, that's not an option here with a solid. if you neglect thermal expansion, which is a tiny, tiny phenomenon that's only important for very long things like Bay Bridge or whatever, okay? So for a solid, Cp and Cv are basically the same thing. There's not this option of having some of the energy sneak out as work. So there really isn't a distinction between Cp and Cv when you're talking about solids or liquids even. So you may wonder, how do we get away when you were doing your first thermo homework, homework 5, you're just using heat capacities and there was no constant pressure, constant volume business. Well, that's because it didn't matter. I mostly gave you solids and liquids to work with, and there doesn't need to be two different heat capacities for that. They're the same thing, okay? So it's only for gases that it matters. Now, if you ever look up a heat capacity for a gas, then you should be very much asking the question, is this Cp or Cv? Because they're very different. The few that I happen to sprinkle in just incidentally up till now were undoubtedly Cp, okay? So generally speaking, if you're working with a sample of gas and you don't confine it in a space, then the only constraint is that atmospheric pressure around it is going to hold it at a constant pressure, okay? So again, when you're looking up the heat capacity of a gas, it's really important to know which type it is. It doesn't matter for solids and liquids. It's essentially the distinction is completely washed out, all right? So let's once again do the same thing where we make a comparison of real world things. Oh, and before I do that, I guess I should show you what the graph looks like. What does Cv, I guess, it doesn't matter, Cv or Cp, what does it look like versus temperature? Now, it appears to be a constant, but remember, in order for it to reach 3R, we have to have the high temperature fully engaged. So it looks like this. It actually asymptotically approaches this value as the vibrational modes are fully unlocked. Okay. So it starts from down here where they're partially melted, and only once you get to the high temperature range where they are fully unlocked does it converge on this value, 3R. Okay? I think I gave you a problem just for giving you some calculus practice. There was a problem on homework 5 where I said that the C as a function of temperature was proportional to T cubed or something like that. Then you can just practice your integration. Do you remember that seemingly random problem? Yeah. Okay, it was just for calculus practice, but I didn't just make it up, okay? It turns out that at very low temperatures, that is the curve, okay? So I try not to make up problems purely just for math practice, so it did have a real world application. We're not going to be worried about that. That was just a math exercise, but again, it grows, and then it becomes constant. So let's make a comparison of real-world materials. I've just been doing this all along the way just so you can see how these models really work in real life. Let's make ourselves a little table. What's the element? Of course, when I'm specifically picking elements that form monatomic solids, I can't pick something if it doesn't actually behave this way chemically. Here's two examples. Aluminum and silver. So these are both things that form monatomic solids at certainly around the room temperature that we live in. And what is the element number on the periodic table? This is 13, and this is 47. Okay? So, then we go to the molar mass, and again, most typically, you can grab it as grams per mole off the periodic table. Here we are once again back to monatomic, so we don't need to worry about the distinction between moles of gas particles versus moles of atoms. So these are just grabbed off the periodic table. Again, if you don't have that handy, what's your best attempt to guess that? You just double it, right? So if you double 13, you'll get what, 26? The actual is 26.98, okay? Not bad, okay? So there are 14 neutrons and 13 protons for a total of 27 things in the nucleus, which means 27 grams per mole roughly. Now, silver is a high enough element that the multiply by 2 doesn't actually quite work. If I multiplied 47 by 2, I'd get 90, whatever that is. I can't do arithmetic. I work in variables. Okay. Here, this is large enough that it needs a few more peacemakers. It actually has not 47 neutrons, but about 60, and that gives us 107.87. And you go from here to here, it's about a factor of 4. Question?
And again, it has more than double because it has to keep it stable because it's a big element.
That's right. So when you get to these gigantic nuclei with lots of protons that would want to fly apart, you need to put in more peacemakers or spacers, which are the neutrons. So neutrons stick to protons and neutrons just fine, but they don't have the electrical charge that would tend to make everything fly apart. Okay, so let's try it. So let's calculate C, and notice here I don't make a distinction, CP versus CV, they're basically the same thing. And this is going to be in joules per kilogram Kelvin, and I'm going to put our model, and then the actual. So what does our model say? It says that basically this is your value. If you're a monatomic solid and you're looking on the mole side, you're basically going to see the same exact value for this. The only difference you'll see on the specific heat side is because, of course, we need to divide by a different molar mass. So remember how this works. We take our molar heat capacity, divide by the molar mass, and we get a specific heat capacity. And again, when you're doing that, remember that this is grams per mole, so you need to do it kilograms per mole. And what do you get? You get 924 here and 231. So no surprise, because the molar mass was 4 times, then the specific heat is about 1/4. Now, what are the actual values? Well, these, I don't have to go to some CRC or some other, the web or some other source. These are literally on your table. On your data page, there is a list of specific heat capacities for several solids and liquids, including these two. So it tells us 900 and 235. Okay? So as you are grabbing for various values of specific heat on homework 5, you may have already grabbed those two. So if you look at them, they're pretty close, right? Not too bad. So how do they compare? Well, aluminum is easier to explain. Aluminum is a little shy. So why might these actual value be a little bit lower than it should be? Looking at this graph. What's that?
Might be temperature higher later on.
That's right, exactly. So apparently for aluminum, room temperature is, you're not fully there yet into the high temperature regime. So you haven't fully unlocked everything yet. And so you haven't gone to as high of a specific heat as you could have, as high of a heat capacity in general. Now this one is harder to explain away because it's a little higher, but I will tell you again that the model is not perfect. One of the things that will happen is if room temperature is about here, some substances have long since plateaued, and so 3R is an excellent approximation. There are other substances that they take a long, long time to climb up to this plateau, and so there you will find that their experimental room temperature value is, this is a bad approximation, because they haven't nearly finished climbing it up to 3R, and in the case of silver, some more advanced effects might cause it to actually plateau out a little higher. So when you take a look at the experimental graphs, you'll see that they do vary a little bit in terms of how rapidly they climb and exactly what value they plateau at, but the law is striking in that everything seems to be more or less asymptoting out at 3R, give or take, after you get to a high enough temperature. Okay? So for us, we won't worry about the exact details of how they climb up to 3R and exactly what value they plateau at. This is going to be good enough for us. So if I ask you to estimate the heat capacity of a monatomic solid, we use this model. Are there any questions on that? Okay, so that takes care of the monatomic solid. I should note that that's actually on your homework number 8. I looked and I double checked. I don't think it's mentioned anywhere on homework 7. So remember when I said homework 7 and 8 kind of bleed together? Here, I happened to talk about this before I finished off the adiabatic process, just because it's nice to go through and do all our counting of our degrees of freedom kind of all sequentially. So we went through everything last time. We went through the monatomic gas, diatomic gas, polyatomic gas, and now monatomic solid. And by the way, if you've gotten the thermo summary sheet, you'll notice this is all on a nice little table in the upper left-hand corner. Okay. So, are there any questions on this before I go to do the adiabatic process? All right, so that's going to be the last ingredient you need for homework number 7. We'll continue using it in homework 8, but there is adiabatic stuff mentioned on homework 7. So if you're holding off on doing those few problems, we'll be able to do them today, after today. So let me remind you about what the adiabatic process is, because I know it's been a few lectures. It's a process in which there is no heat flow. Why is there no heat flow? Either you've really well thermally insulated the container, or you just happen to do what you're doing so fast that heat doesn't have a chance to flow. This is where the energy of the gas is traded solely by work. Okay? That is how you are achieving any energy and temperature change of the gas is solely by work. The examples I gave were the bike pump, where you rapidly compress the air and it heats up, or popping the top of a soda bottle, where you get that little mist on the top after you've popped it because you've rapidly expanded the gas using work and the temperature has dropped. So, if we're going back, you have from a couple lectures ago a table we were filling out with a couple items missing. Let's go and fill them in. So one of the things that we wrote down at the time was that the work done is equal to minus the change in internal energy, which of course was a complete stop back then because we didn't know anything about the internal energy function, and now we know all about that. So we can just go ahead and fill that in, okay? So I'm going to go ahead and just write this in. So I'm going to go ahead and put it in, and I'm going to put it in a kind of a funny way. I'm going to put it in like this. Now you might say, CV, what's that doing in there? This is not an isochoric process, this is an adiabatic process. Let me justify that. So an isochoric process as we learned, is one in which no work is done. And the appropriate expression for Q would be NCV delta T. Now we are working on an adiabatic process in which there is no heat flow and it's all work. So where do I get off kind of conflating the two? Well, I get off on conflating the two because as long as the energy change is the same, so I have the same change in internal energy and same change in temperature, it doesn't really matter how I do it. So I can set these two equal to each other, and I get this. So it's just basically saying that there's two different ways that I can get between the same two energies. And I guess I can draw it to show you what it looks like. Here's PV. Here's my PV graph. Here's one temperature. Here's a higher temperature. So one way I can get between these two temperatures is isochorically. So no change in volume, no area under the curve. And the other way is adiabatically, which looks like this. And of course, it doesn't really matter. Once I arrive at a certain isotherm, I've changed the energy by so and so much. Okay? So really what this is a shorthand for not wanting to put in the fact that CV is F over 2R at low and medium temperatures, and CV is F plus 1 over 2R at high temperatures. If I put those in, you might like it better because CV isn't mentioned explicitly, so it doesn't trip you up that this is not an isochoric process. And it just has our raw statement of total energy, right? But keep in mind, what am I doing here? I'm not saying that this is Q, okay? I'm just exploiting the fact that the Q, if I did this change isochorically, would be equivalent to the minus the work I need to do to change that same change, make that same change in energy, doing a completely different method, okay? So I'm basically saying that the work done in this process happens to be equal to the negative of the heat that you would have to do during a completely different way. Okay? So that's one expression for the work, like so. And let me give you a couple other very common ways to express this. So one of the things we've talked about is gamma. Its usefulness has not really become apparent yet. We've just kind of dragged it along. Well, gamma, the adiabatic process is the realm of gamma. We use gamma a lot for that. And in fact, one of the things that we like to do is anything that's associated with the adiabatic process, we try to frame it in terms of gamma instead. Okay? So let me calculate here. The Cp is Cv plus R, assuming we're working with gases. Like so. And I can solve for Cv here. And I can put in Cv instead as terms of something with gamma, and then we can kind of think of as gamma as the thing that goes with adiabatic processes. So I'll go ahead and put that in right here. So there's a completely equivalent algebraic way of writing this thing. Okay? The only thing I've done is express it in terms of gamma. Also, that affords me the opportunity, N R delta T can be expressed with the ideal gas law as P final V final minus P initial V initial. So that's yet another way to express the work. Here I'm giving you three different choices, all of which are completely equivalent algebraically And as far as which one you use, I think they're all available on the equation sheet. It's just a matter of which information you happen to have more handy. I like the second two forms because they use gamma, which is just painting over the weirdness of having CV in there, because it's not isochoric. We start to associate gamma with the adiabatic process. And I especially like the third one because it's most handy for when you're actually trying to find the area under the curve, right? So when you're actually trying to find the work, which is the area under the PV graph, oftentimes you have information about the pressures and volumes that you're working with, because of course those can be read directly off the graph. Does that make sense? Okay, so we're pretty much now all set with calculating the work. There's your formulas, pick your favorite. And now we have to talk about what's conserved. So, of course, if we talk about P, V, and T, those are basically the three ingredients of the ideal gas law. We had three processes, each of which took a turn leaving one of those three constant, right? We had the isobaric, which was the pressure was constant, isochoric, where the volume was constant, and isothermal, where temperature was constant. None of these are constant, okay? So we can't come up with something from the ideal gas law where we'd have some ratio of these two being constant. They all change. So here, by the way, I guess I should draw it fresh. PV, this is what, for instance, an adiabatic expansion looks like. So let me remind you, I know this was a couple lectures at this point, why it looks like this. Remember that work is equal to minus delta E. So if we have positive work, which we do in this drawing, positive area under the curve, we must have negative change in energy. So we have positive work, but the internal energy and temperature decrease. So in this case, what have I drawn? I've drawn an adiabatic expansion. What's happening is I have gas. Energy is going out as work. Remember, work being positive means energy going out. And since nothing goes back in to fill it, we're of course going to deplete the energy and lower the temperature of the gas because we're passing energy out as work. So you see that we do have positive area under the curve, and we are dropping to a lower isotherm, right? So this does have positive area under the curve, and it's dropping to a lower temperature isotherm than it started with initially. Now if P, V, and T all change, you might be skeptical that we could even find some relationship between them that is conserved, but that's what I aim to do. So this is the last little piece of the puzzle we need for the adiabatic process. So let's find the area under the curve. That's what this is, right? Now, if we go ahead and plug in nRT over V, that's the ideal gas law, again, we know that T changes and V changes, so nothing can be factored out here except possibly the NR, right? So we run into a roadblock. However, this is where we come in the back door and we realize, hey, we already know the work. We had the back door of knowing these internal energy functions at this point, right? So we found the work already. So what I'm going to do is I'm going to, with the internal energy function, the internal, I guess I'll say just E function, I can come in and fill in this side. I'll just pick one of these, which I know is going to be the handiest. Minus nr delta t over gamma minus 1, okay? Now at this point, my mission becomes unclear. What am I actually solving for? Well, at this point, I just kind of go for it and see what I can get, okay? So does anything useful come out of manipulating this? I'm not really looking for the work because I already know the work. I've come in the back door and I found the work using the internal energy. So here's my suggestion. First, let's strip off the integration. And of course, that is going to make this, let me do it in a different color so you can see what I'm doing. So I'm going to peel back the integration, and of course, then this will become a small change in temperature, right? Is that a step you guys are comfortable with? No?
How did you do this?
How did I do this? Okay. All right. So I have integral of dx. What is integral of dx? X. Okay. What if I take off this? I get dx. I don't know. Yeah.
In this case, you're taking an integral in terms of v, not in terms of t.
Right. Okay. Here's another example. Okay. Let's see if this helps. So I have this equation right here. Good old mc delta t, right? Yes?
Yes.
Okay. Now you guys did one problem where the c itself was a function of temperature. So what we had to do is whatever c is at the moment, I make a small change to the temperature and I get a small, and that's caused by a small change in heat. Yes? And then you integrate this. That was that problem I was referring to earlier today. Do you remember doing this? What's that? What's that? I don't remember if it was a challenge problem, but it was the c was a function of t. So the whole point was here is that if c is a function of t, then I'm basically at a certain temperature. I add a tiny little bit of heat and make a tiny little temperature change because of it. But because I'm doing it just a tiny little change, basically my c hasn't had a chance to change out from under me yet, right? Okay. So then I say, okay, now I'm going to make a bunch of those little dq's, and this is going to integrate to q, and then here I'm going to have to, of course, figure out what is my c as a function of t so I can integrate, right? I'm sure that this was a problem that you did, okay? So all I'm doing is saying, let's peel it back one step. So let's go from this to this. So I don't want to go over a bunch of different volumes. I want to be pretty much at one volume and one temperature. I want to make a tiny little change to the volume, and that's going to involve a tiny little change to the temperature. I'm just peeling back the integration to what am I integrating? That's what integration means, right? It's adding a bunch of small steps, and I don't want to add a bunch of small steps. I just want to look at one small step. Okay? Okay, so anyways, this is a calculus matter, so let's not dwell on it too much, but you can do this. If you don't want to add up all your little steps of dV, you're not going to get a big temperature change. You're just going to get a tiny little temperature change dt. Okay? So now let's kind of play around with it. Let me rewrite it here so it's clean. nr dt over gamma minus 1, nRT over v dv. So what I'm saying is that if I make a tiny volume change, I will make a tiny temperature change. I'm going to cancel the common stuff, nr, nr. And now, if I want to do anything to it, I'm going to use the opportunity of the integration stripped off to shuffle around the terms in a way that's more favorable to eventually integrating again. So I'm going to group the t over here, and I'm going to group the v over here. I'm basically doing, what do you call this, separation of variables? Some math lingo, okay? So this I can do. I can get somewhere by doing this. It's unclear where I'm going, but as far as legal math, I know you guys are skeptical, but it is legal, okay? And I want to integrate now both sides, and let's see where we land. So integral of dt over t, ln of t. And I don't want to plus c crap, that's not for physics. So there's no plus c in the real world, so I put in the integration bounds. Obviously, by definition, what am I integrating? T initial to t final, right? And I do it as a ratio. Is that okay? I do it as a ratio, or do I have to do the ln of minus ratio, all that stuff? All right. Okay. So again, I'm hoping that if you don't quite see the math, that you can fill in the gaps. So here's what I get. Now I use the property where you have a natural log. The exponent becomes the multiplier. Is that a thing that is known? Okay. So I'm going to haul this whole thing up here as an exponent. And I don't like the minus, so I'm going to just take care of that right away. So that I can just do by flipping the ratio. Yes? And here I haven't had any change. Now it should be obvious what to do next. I don't need these ln's. Okay? And let's see where we landed. We get something. I know it's unclear where we're headed, but we got something.
Do you mean, sorry, in the exponents, do you mean 1 minus gamma?
No, I flipped. To get rid of the negative, I flipped the temperature ratio. Okay. So here's what I get: T initial over T final to the 1 to the gamma minus 1 equals V final over V initial. Now these powers are super annoying, right? If it's a squared, you just take the square root, right? Do you guys know how to reverse powers that are super annoying? Just raise it to the 1 over, right? Yes? Okay, so if you want to get rid of x to the 3 halves, you raise it to the 2/3 power. Okay, so let's do that. So I'm just going to move the power over there. And then I'm going to solve for all the initial stuff on one side and all the final stuff on the other. And I get this. Now this is not seemingly remarkable until you notice that it's the exact same stuff on both sides. I've just found a conserved quantity. Okay? So I've just found out that TV to the gamma minus 1 is conserved for an adiabatic process. So we were looking for something like that. We were looking for some relationship between P, V, and T, even though they're all changing. Can we package them up in some way so that when we undergo an adiabatic process, we can actually say that something is conserved? We've just found that. So how is this helpful? If you know the T and V that you started with and the T that you end with, you can solve for the volume that you must have ended with. Okay? Does that make sense?
As long as you know CP and CP.
What's that?
As long as you know your CP and CP.
Oh, well, you don't even need that? Oh, yeah, we need it for gamma. You need to know the gamma, right? So gamma, you can see why gamma is so useful for this stuff, because it appears as an exponent. It's gamma minus 1. Let's do one more thing. This is a relationship between T and V, right? Between these two. But it's not so useful quite as directly useful. The PV diagram relates P and V, right? So let's see if we can swap out the T and replace it with a P. Then we have information that would be directly relevant to the PV diagram. So I'm going to get rid of the T and put in PV over NR. Really, what I'm doing here is swapping out the T for a P. So, what do I get? NR's cancel. And, coolly enough, this V initial is going to add the extra thing here, so the -1 goes away. So I can kill this if by that fills in that one. So I have P initial, V initial to the gamma is P final, V final to the gamma. So I have another quantity, or another way of expressing that quantity that's conserved for an adiabatic process. P times V to the gamma power. Yes, super awkward, but it is conserved. Does that make sense? Question?
Is there a way of algebraically relating that guy to the bottom word equation?
What, that guy meaning what?
The conserved quantity.
Back to
the bottom word equation. It says P final, V final minus P initial, V initial.
well, not really, because this is P times V to a power, which is different from P times V to the first power, right? So it's a totally different thing. It's something that we use when we're looking at a conserved quantity. Question?
What is PV to the gamma, or sorry, TV to the gamma -1? What does that actually mean? Like, what is it? Oh, okay.
A quantity which is conserved for an adiabatic process. I don't think it has any physical meaning beyond that. Okay. If you want what it means on the graph, that we can do. If PV to the gamma is a constant during any adiabatic process, that tells us solving P is proportional to 1 over V to the gamma. Now gamma, of course, is Cp over Cv, so that's greater than 1. So what we've actually just found is the shape of this curve. Okay? So the isotherms, for comparison, the isotherm, PV equals nRT, T was a constant for an isotherm, right? So solving this, P is a constant over V to the first power, right? So that gave us these shapes. These are proportional to 1 over V. But we have just found for an adiabatic process, it's a curve where it's 1 over V to a higher power, right? So those are steeper, right? Y equals 1 over x squared is steeper than y equals 1 over x, yes? So, in fact, let's go ahead and make ourselves a PV diagram. We can mark ourselves off a bunch of isotherms like this. These are the isotherms. They're proportional to 1 over V. That's why they're curved like that. They're like your classic y equals 1 over x functions. But we can also put ourselves a bunch of what we call adiabats. Those are steeper. Those fall off much quicker. These are our adiabats, which are proportional to 1 over V to the gamma. So these are really important because they basically give us the cross-hatching or the grid by which to move around on the PV diagram, okay? So we have these lanes. Now we do have, of course, our horizontal and vertical lanes. What's the horizontal process called again? isobaric. What are the vertical lanes called? Isochoric. But now we have two other lanes, right? We can move along an isotherm or move along an adiabat. So we have lots of different options for how we move around on this graph. The adiabats, if you know the initial pressure and initial volume that you start with, and let's say you know the final pressure, then you can actually, using this relationship, figure out what final volume must you have ended at. That's the most useful application of knowing that this is conserved, is being able to know both, out of the 3 ingredients, or out of the 4 ingredients, the 2 pressures and the 2 volumes, if you know 3 of them, you can immediately get a 4th. Okay, so that'll close out homework number 7, and we'll do some more stuff. We'll start talking about car engines on Friday.